Uh, dilations. Here's what I want to say about dilations before we jump into it. This is, you know how to do this already. You really do. All this is talking about, dilations refer to the process of taking a shape and either enlarging it or contracting it. Okay? There's a mathematical way we go about this, and it involves the math that you've been practicing all chapter. I just need to sort of put it all together, help you put it all together into this last topic. Dilation, to put things in context here, a dilation is what we call a non-rigid transformation. We can go back a while in the class. Remember, we spent some time talking about the rigid transformations, the ways that we can take a shape in the XY plane and move it around, right? But keep it the same. So the result, the final shape after it's been moved is congruent to the original shape before it was moved. Remember, we said that the pre-image and the image would be congruent. What were the three rigid types of transformations we talked about? What's one of them? A rotation. Sure, we can take an object and we can rotate it about a point in the plane. What's another one? Reflection. We can reflect it over a line, sure. And then the last one? Translation, or a slide. We can slide it along, right? Okay, so dilation is like those, similar to those, but different in the sense that the final result and the original result are going to be scale versions of each other, not the same size. So they'll be similar but not congruent. Okay? And that's what I just said. So a couple things here now. The dilation, when we talk about a dilation in math, we always refer to what's called the center of the dilation, the center C. Think of that as, on the next couple slides, this will make more sense. But think of the center of the dilation as being a point way in the distance, way in the very distance. Think of it as being the vanishing point. We call it at infinity. Of course, it's not at infinity, but it's where everything would sort of recede into a single point, right? Think about a dilation as an object it's either coming towards you from that point or receding into the distance towards that point. Okay? One or the other. It's always going to look like one or the other. It's kind of a good trick, way to visualize this. So, like before, we're going to say that the original point, the pre-image, is going to be P, right? And the image is P prime. Okay, so we start with P, and that's going to be blue in all the pictures we look at here in this slideshow. And then we end up at P prime, okay, which will be red in all the cases. If P is not the center of the dilation, so it's not sitting right on that point, then the image point P prime is going to lie on the line CP. And we'll see that also. Okay. We'll also see then that the scale factor, which we're going to call K, the scale factor K just refers to by what factor is the final shape growing or shrinking relative to the original shape, right? So what would we multiply it by to get the result? The way we find that is we're just going to calculate the ratio of the distance from the center of the dilation to P prime, right? The final point after the dilation, divided by the distance from the center of the dilation to the original position of the point. And this will all make sense when we look at it in a picture, I promise you. Okay, so let's do that. Let's take an example. So here's the center C. Now, do you see what I mean by kind of, two shapes that are either moving towards you from infinity or receding towards infinity? In this case, if we're starting with the blue and we're ending up with the red, you can't see the primes very well, but these are the primes. P prime, Q prime, R prime. If we're starting with the blue and moving to the red, you see that this one kind of looks, if you think of it as like a movie, it's moving away from you towards that vanishing point. Does that make sense? Can everybody kind of see that? I mean, you don't have to think it that way. I just think it's helpful. But notice that if I were to extend the lines from C to P, so those lines go forever, right? Like in this case, notice that the prime versions, after the dilation, those points are also going to be on that line, aren't they? Okay? So this is clearly, we can just see from the picture that this is a reduction and not an enlargement. Right? We start blue and end up red, and the red is clearly a smaller triangle than the blue one is. Well, how much? To find out, all we have to do is just compare those distances. The distance from the vanishing point to the original position of P, the pre-image, to the vanishing point to the final image of P, P prime. Right? So CP prime in this case is 3. So the final distance over the original distance being 6. 3 over 6 gives us 1/2. That's our scale factor. Why is that 1/2 significant? How does it relate to these two shapes? What do you think?
That's how much it shrunk.
Yeah, the final version is 1/2 as big as the original version of that triangle. Okay? So if we want to find out the length of a side, for example, we could just multiply the original length by 1/2 to get the final length. Okay? Because that scale factor, as we've seen all through the chapter, that scale factor is the ratio of any two corresponding parts, right? Final to original. So for example, Q prime P prime over QP, the ratio of those corresponding parts, 1/2, for sure. What about the perimeters? Sure. That's a linear measurement. So the red perimeter divided by the blue perimeter, 1/2, right? Every linear measurement between the original and the final is going to be related by that scale factor. Okay? Let's look at another example. Okay, that was a reduction. Let's look at an enlargement. If we're starting blue and ending red, so it looks like this blue shape is moving sort of towards us from point C, right? We see that? Okay. What about the scale factor? All I have to do is find, now this one got kind of messed up. The 5 doesn't show up. 5 ended up down there. But that distance is supposed to be 5. So the final distance from the vanishing point to a point, in this case P prime, is 5. The original distance was only 2. And so therefore the scale factor is 5 over 2. Right? Makes sense. It's an enlargement. Now, maybe I kind of breezed over this a little fast, but from this previous slide, does it make sense to you that a dilation, in order to get a dilation that's a reduction, we're going to be multiplying the original distances by a fraction that's less than 1, aren't we, to make them smaller? Like we had 1/2, I think, in this case. Right? We multiplied the original distances by 1/2 to get the final distances, making them half as big, smaller. So you know then that the scale factor K has to be between 0 and 1 if it's a reduction. Now, if it's an enlargement, we're going to be multiplying by a number bigger than 1 to get a bigger answer, right? So in that case, K would have to be greater than 1. Okay? So in this case, as expected, the final distance of 5 divided by the original distance of 2 gives us a scale factor of 5/2. Makes sense, right? That's bigger than 1. It's an enlargement. How much bigger? 5/2, 2.5, right? All of these sides are 2.5 bigger than the corresponding sides in the original. Okay? Questions? Does that make sense? How about that one? Identify the dilation, find its scale factor. If we're starting blue and ending red, is this going to be a reduction or an enlargement? Reduction. Okay. If we find the distances to corresponding points, it looks like the distances from C to P and C to P prime are 3 and 2. Without even thinking about it too much, if I've got numbers 3 and 2 that need to go in the numerator and the denominator, and I can see that it's a reduction, which one obviously has to go on top? The 2. Yeah, because I have to make a fraction that's less than 1. So the denominator, the bottom, has to be bigger than the top, right? Okay. All right. How about that? Starting blue, ending red. Enlargement. The distances between P and P prime are 2 and 1, so the ratio must be 2 over 1. Right? And that makes sense. The final distance is 2 divided by the original is 1. 2 over 1 just gives us back 2. Okay?
I sneezed on my shoulder.
Uh-oh. So scale factor's 2. Everything grew by a factor of 2. Double. Okay, last part. So the last issue that comes up with dilations is if you're in a coordinate plane, so we're putting this in the XY plane, then that's a convenient way to look at dilations. Now the most convenient way to do that is if we let the center be at the origin, right at the point 0, 0. If we do that, then whether it's a reduction or an enlargement, it doesn't matter. The distance from the center to x and y, the original coordinates, all I'm going to have to do, of course, then, if I want to find the new coordinates after the dilation, is multiply both the x and y values by k, the scale factor, because it's going to proportionally either pull that point towards the origin, if it's a reduction, or push it away from the origin, if it's an enlargement, by the same amount, by the same factor, right? Let's look at one example of that. So what about this here? Now, we'll see a graph of this rectangle. We're starting with rectangle ABCD that has these coordinates for the 4 points, A, B, C, and D, and we'll see a graph of this. Now, if the origin is going to be the center of the dilation, so in this case, the rectangle is either going to be pushed in towards the origin if it's a reduction or pulled out away from it if it's an enlargement. If the scale factor is 1/2, it'd be a reduction, right? What does that tell us about all of these coordinates then? If I want to find the new coordinates? Halfway to the origin. Yeah, let's see that. So here's the original, right? Let's take, for example, D and D prime. We start off with D. Let's look at one of the vertices. D has the coordinates, it looks like over 2 and up 4, right? So if the scale factor, if we know that K, if we know that K equals 1/2, then when we multiply those coordinates by 1/2 to push them halfway in towards the origin, what am I going to get for my results for D prime? 1/2 times 2 is 1, and 1/2 times 4 is, and we can see that. Look, we go over 1 and up 2 to get to D prime. Okay. Now, what if the scale factor had been, instead of being 1/2, what if K had been 3/2? And what if K had been 3/2? Then we would have been, instead of sucking this blue shape in towards the origin, we would have been pushing it away from the origin and making it bigger, right? So if I had multiplied all this, let's take this one point right here, point D. If I had multiplied that by 3/2, what's 3/2 times 2? 3, right? So we would have been over 3, and instead of 4, what's 3/2 times 4? 6. So we would have been over 3 and up 6 right there. So that would have been, notice that's still on that line, right? Whoops. We would have been right there for that upper corner. Make sense? Yeah. What about this? What about point A? So that would have been D prime. What about point A? Instead of going over 2 and up 2, if I multiply by 3/2, wouldn't I have gone over 3 and up 3? So it would have been right there. That would have been that left side of the rectangle if I had pushed it outward by a factor of 3/2. Did I make a mistake? That's correct. Okay. So instead of it being right here, right, this is the one we're talking about. That side would have gone up to there. You got it bigger. Okay. Make sense? Okay, here's what I'm asking you to do. I want you to go practice this while it's fresh in your mind. So I'm going to take you to a lab. I think we can find the lab. Even if you're not on 8-7 yet, pause what you're doing on your current assignment and just do a couple problems from 8-7 to make sure this makes sense. And then you go back and work on the other one.